Welcome to Galactic Talk Show. My name is Nanekia JC, and I'm the host. Joining me here today is Mr. Charles Dazi.
As usual, we're always here.
You're welcome to today's
Thank you.
meeting. So today's topic is why objects of different masses fall at the same rate. Are you getting it? Why objects of different masses fall at the same rate. Stay tuned, relax, get some popcorn, a book and a pen, and join us for today's discussion. So, why objects of different masses fall at the same rate? First of all, someone would like to find out, what is a mass?
Should I say mass is just the material contents, right? It's just you. It's just you. So your mass doesn't change. That is why we sometimes equate mass to weight. Mass is always what is inside you, what you made up of. But weight is the one that's working on mass. So sometimes you can have a different weight at the equator, and then you can have a different weight in the temperate regions. Why is that so? It's because at the equator, the earth is spinning and it's trying to throw you away. But gravity is also keeping you here. So once those things cancel out, you become like you lose a bit of weight. So you might be there and be like, oh, I've lost weight. When I came back from US, I came to Ghana and whoa, I've lost some weight. You haven't lost any weight. You still have that same mass in you.
Okay.
Right. But when you travel back, you realize that, oh, but I'm back to the same weight. Why? Because you are at the equator. And the equator was, the circumference where the equator, so the earth is throwing you away and gravity is holding you. So you are losing some weight there. So that's just about when we talk about mass. It's what is in you. It doesn't change. So unless you are eating more and you are gaining more mass, or you are exercising more and then you are gaining more mass.
Okay.
You don't. As for the weight there, it's always acting on you. Yeah, the gravity is always acting on you. So that when we talk about mass, that's what comes into play. Yeah.
Okay. So apart from using a human being to explain mass, can we use something else? Because I feel like your explanation of mass over here talks about weight.
No, I was just trying to equate the two because people kind of put the two together.
Mass and weight.
Okay. And I'm just trying to say the mass is what is inside you. So it's like you pick a phone and because it is pressing on your hand, it is being weighed upon. But what is in the phone doesn't change at all. So you measure the mass, but you use sort of a spring to measure the weight. But what is inside the phone doesn't change.
So if I'm guessing, it's the mass is the content.
The content.
And the weight is how heavy or light the content is.
As in based on gravity, based on the force that is acting on it.
Okay.
So your mass doesn't change. Your mass will always be the same. That's what unless you are training yourself and then you have a higher body mass. So they don't when the weightlifters they say a higher body mass, not a higher body weight.
Okay.
Your mass will expand, you become bigger and all that. Sometimes people also try to confuse it with density because density is the amount of that thing that is in you. You understand? The measure of the amount of that thing that is in you. That is what is density. That's why it's mass over volume. So when you have a smaller body that has a lot of things inside, right? It is more dense. And so it has a greater mass and a smaller volume, right? But when you have a bigger volume, a huge something, and then you put just a few things inside, the mass is lighter and the density is also lighter. So definitely density is equivalent to mass, as in, how do I say it? You are the science student. Give me that term. That term that you guys use that kind of X thing. Y is proportional to X. Density is proportional to mass. We are trying to get back to school days. Okay. Yeah. Now to what we spoke about, the topic. That topic that has been a subject of a lot of debate in scientists, even as at now. People are still battling with it, and today we want to clear it. Galaxy want to clear that issue. Today we have to end that issue. Okay. Let's go back into history. Aristotle. Aristotle is known for the person who brought up this whole idea of fallen objects. But funny enough, Aristotle, most of his postulates were later we found out that they were not really science based. They when as soon as you do the experiment, the scientific methods, you realize that as Aristotle didn't say he didn't really contribute much, but his name is there. I mean, you all know Aristotle. So he said, right, fallen objects, the rate at which an object falls is directly proportional to its mass.
Okay.
So the bigger the mass, the faster it falls, or it falls at a high rate. So if I'm 10 times heavier than you, I have to fall 10 times faster than you.
Yeah.
And nobody said anything. Everybody believed it at that time. One day Galileo woke up one day and Galileo said, look, I need to run this experiment because there hasn't been any scientific method. Somebody woke up and said something, and that's what we live by. And it looks like once you start running experiments, you can see there are some different things. Decided to go up a building, decided to drop 2 balls. Right. Now those balls, at least a bit of density, not like a feather that is affected by air. So he dropped the 2 balls and realized that they fell like this one didn't fall 10 times faster and left this one. Like they fell like coming at the same rate, and then they fell. So it made Aristotle's work. No, we don't need that work again. Okay. So now something has come up. So how do we work around this new idea that has come that something is beginning to fall at the same rate? Okay. In the 70s, when the discovery of the moon came into place and the Apollo mission started, the Apollo 15 mission, they actually took a feather to space and a hammer to space or so, a ratchet or so. And then they stood there to conduct the experiment because there's no air resistance. There's nothing there like that. And funny enough, the feather and then the ratchet fell at the same rate. It came down the same time. Right. So it became sort of a subject of discussion. So what is actually the cause of all this? And it came to a realization that an object falling is actually directly proportional to gravity.
Okay.
Okay, so a heavier object is attracted more by gravity. A lighter object gets a less attraction. So let me give you an example so that it becomes easier for you, so you probably understand. When you have you have a huge stone and a smaller stone, and you are supposed to push it down the hill, which one requires more energy?
Bigger one.
The bigger one, right? So you're going to push more, right? So it's in equivalence to the fact that when you have a bigger body and a smaller body, what gravity is doing is that it is pulling both of them. But then because this is bigger, gravity is pulling it more to itself, right? But they fall at the same rate. Now, when we get to the same rate, we'll talk about at what acceleration does an object fall.
Okay. Before you come in with that, I would like to find out a few things. So talking about Aristotle and then Galileo.
Yeah.
From your previous submission, it kind of looked like actually what Aristotle said is true.
You were talking about mass.
He was talking about the masses of the object.
But it has nothing to do with them. It has everything to do with gravity.
Okay.
Gravity pulls on a heavier object. That is all. When it has more sort of, should I say weight?
But over here, we are also talking about mass.
Yeah.
So, mass of objects.
Yes.
Let's say you have a balloon,
Yes.
and then someone has a bag of sand,
Okay.
and you are to release all at a goal,
Yeah.
okay, from, let's say, a 4-story building.
Good.
Yes. We are talking about mass over here.
Okay.
And the mass says that they all have to fall at the same rate.
Not the mass. That is what Galileo said.
Yes. They all have to fall at the same rate.
Good.
Yes. So will they fall at the same rate as Aristotle said, or it's going to be as Galileo said? That's the difference I want you to
Okay,
make.
so in the absence of air resistance, balloon will definitely be affected by. We're talking about bodies that have a bit of density that is falling. And I made mention of the fact that because he equated it to mass, are you telling me that if I have more mass than you, as in 10 times more mass, I'm going to fall at the same 10 times faster than you?
Okay. I think so.
I'll fall 10 times faster than you.
Not 10 times, but the possibility of you falling faster.
Good.
It will be faster than...
When we talk about rate,
Okay.
rate has to do with what time.
Okay.
That's why I said I was jumping you there. Now, what is the acceleration due to gravity on Earth?
I don't know.
9.8 meters per second squared, right? Or you squeeze 10 meters per second squared.
10 meters per
Second squared.
Okay.
Per second squared, because it's acceleration. Okay, so I take two bodies. Right? I take two bodies. Right? And I'm supposed to drop them. Right? So, or even one body, okay, I'm dropping this. When I drop, it's kind of starting from 0. Right? So it moves at a speed of what? 9.8 meters per second in 1 second.
Okay.
So that becomes 9.8 meters per second squared, because it's accelerating. Now, speed has only one s, which is the time. Now, acceleration has the double. So it drops 9.8 meters per second in 1 second. Drops again 9.8 meters per second in 2 seconds.
Okay. So
it is increasing. So from 9.8, or let's just use 10, because so we can do the calculation. So it says 10 drops 10 meters per second in a speed. It's coming. But then it is accelerating because it's coming down. It's increasing speed that's why you call it acceleration due to gravity, not speed due to gravity. So at each second, the speed will change by 10 meters per second. So in the first second, it comes at a speed of 10 meters per second. Second, it goes to 20 meters per second. Third second, it goes to 30 meters per second. Right?
Yeah.
So that is what we are terming as rates.
Okay.
Right? So it is falling like it's increasing its speed as it's falling. Regardless, you see how it's like. So I brought these two here, like, to do the experiments. We have a T-roll here and a comfort ball here. Right. So you have them coming down like that. So maybe this is 5 times heavier. But then when you look at them,
Okay.
right, this didn't fall 10 times faster. They came probably at the same rate, traveling at the same speed into acceleration, right? So Einstein thought about it this way. So today I've mentioned Aristotle, I've mentioned Galileo, and I'm mentioning the man. I call him the man because he always think further. So he brought it to the universe, on the universal level. So what's happening on the universal level? Okay, so I am sitting in a spaceship and I'm traveling at a speed that the gravity is working on me. So gravity is pushing 10 meters per second squared on me, exerting that force. And I'm traveling at that same speed, 10 meters per second squared, meet all that, accelerating, which is the word I'm accelerating to meet it. Just like the floor is coming to you in the space shuttle. So it will look like you are standing, the floor has come to you, and you are actually being at the same speed that is coming. So you are stuck there. Like you're stuck in the spacecraft because it's met you there. So if you are elevating and you are moving at the same speed, it will hit you to touch your leg, and then you guys will be moving up speed together. So Einstein said this, and it's very fascinating. And I've always said I've dropped the mic from Einstein. He said, look, if a space shuttle was to behave as the Earth, or the Earth takes up the same attitude as a space shuttle, then the way gravity works on Earth is indistinguishable from the space shuttle that is traveling at that same speed, hitting that same that same speed, hitting that same. So it's indistinguishable from what gravity is doing on Earth and what you are doing in the spacecraft. Yes. And that is what they call the equivalence principle. And it's very interesting. Einstein was, and he even went on to say this, and this is where it's most interesting, and it's very nice to know. He said, when you sit in a spacecraft moving up, accelerating up, and you stand on one side of the spacecraft and you light up a torch and you're going to space, the light is going to bend.
Oh.
You look at, you see the light just bend in the spacecraft. Yeah. It just keeps bending like that. So he comes down back and says that. So if Earth was in that motion as a spacecraft, then gravity will definitely bend light when it comes on Earth. And it's very interesting. As I said, when he brought that up, I read it, I was like, mic drop for him. I've dropped my mic for him. I've dropped my phone for him. Because that is some serious work done there. Okay. So basically, it falls at the same rate at 9.8 meters per second at each second.
At each second.
Yes. So it becomes 9.8 meters per second squared, 10 meters per second squared, 20 meters per second squared, 30 meters per second is coming down. So it's coming with that speed. So that explains that things fall at the same rate due to gravity, because gravity pulls higher on bigger objects than smaller objects.
Okay.
Not necessarily its mass. Because as soon as you talk about mass, they will tell you, okay, so if the mass is 10 times, then you have to fall 10 times faster than me. But this time, we want to talk about gravity. And gravity acts the same on everybody.
Okay.
So that kills it.
So that means Galileo's,
Aristotle.
Aristotle's theory regarding different masses of objects falling at the same rate doesn't stand.
We threw it away. It didn't stand.
Okay.
It became, we don't want it again. The calculations didn't work well. We always realized that it was gravity that was doing the work. As I said, when you are pushing something down the hill, you need much more strength to push it down than a smaller one. So it's the same. Gravity is just a lazy guy. He's just looking for the bigger guy to pull on. And the smaller guy is there, you take his time with them. So that basically explains how things fall at the same rate.
Okay.
Not necessarily the masses, but
it's the gravity
that pulls on it. So.
All right. So talking about gravity.
Good.
One would like to know, what is gravity? Because if gravity is pulling things to fall at the same rate, at the same time, then what is gravity?
So gravity is like this. As I said, bigger objects tend to pull things closer to them. So bet me if we carry you to Jupiter, you can't walk.
Okay.
Why? Because gravity, Jupiter is so huge that it pulls you down. So you just be stuck there. You can't move. You can't raise your leg because the weight will be on you too much. Whereas you go to the moon, you are hopping. You understand? Because the moon is of a lighter mass. Right? So the gravity there is less. So you just be hopping. But then I always say that all these things come with evolution. So when people start settling down on the moon and people start having kids on the moon and they start growing and growing and growing, they'll get used to walking straight on the moon. When you bring them down on Earth, they can't walk. Over these years, you have got used to your gravity. So when you go on the moon, you're hopping. So when somebody comes from the moon, you can't work here. You understand? So when you spend years, you get used to it. Yeah, when you come here, so gravity has to do with the pull from the body that pulls you down. So the bigger the body, the higher the gravity. So that's basically it.
Okay, so we've had this discussion, and right now, we know that we are going with the sayings or what Einstein actually came up with,
Yes.
and not that of Aristotle, and not that of Galileo.
Yeah. I mean, Galileo came to modify it a bit.
Let's say he's the middleman.
Exactly.
Okay.
So he made it aware that, look, you guys, Aristotle is not saying something right.
All right.
So, yes.
Okay. Okay, so thank you so much for today's episode.
I'm very grateful to still be here and still giving the Galaxy talk.
Okay. Yeah. So right now we know why objects fall at the same rate. And we get to know that with or without them being the same mass, or even with them being different mass, it is not just about that makes them fall. It is gravity. So they fall at the same rate because of gravity. And I know you've learned something out of today's podcast. So thank you all for joining, and see you on our next podcast.